Welcome. This video will guide you through using SQLAlchemy, a powerful Python ORM, with Snowflake, a leading cloud data warehouse. SQLAlchemy, a powerful Python ORM with Snowflake, a leading cloud data warehouse. We'll focus on ORM-style workflows, allowing you to interact with Snowflake databases using Python objects, abstracting away complex SQL. This integration simplifies data engineering, data science, and ETL processes. As of November 2025, this is a mature and stable approach. SQLAlchemy is a powerful Python library that provides a high-level interface for interacting with databases. Instead of writing complex SQL queries, you can define database tables as Python classes, map relationships between them, and perform queries using familiar object-oriented methods. This approach makes database operations more intuitive. For example, you can create models like restaurant and menu item as shown here, with columns and relationships defined in Python code. Using SQLAlchemy with Snowflake streamlines development by providing a consistent ORM layer. This improves code readability and maintainability compared to raw SQL, especially for complex data models. The data flow shows how the ORM connects your application logic to the database. To begin setting up SQLAlchemy with Snowflake, you'll need to install the necessary packages. The required packages are SQLAlchemy and Snowflake SQLAlchemy. Install them using the pip command, pip install SQLAlchemy Snowflake Alchemy. The Snowflake SQLAlchemy package acts as the dialect, translating SQLAlchemy operations into Snowflake-specific SQL. It supports SQLAlchemy version 2.0 and later for modern workflows. You'll need to configure a connection string, including your Snowflake account details, database, schema, and warehouse. Here's an example connection string, snowflake/user password account.snowflakecomputing.com/database/schema warehouse equals warehouse name. Remember to replace the placeholders with your actual Snowflake credentials for secure connection. In this section, we'll define database tables as Python classes using SQLAlchemy's ORM. This involves inheriting from declarative base and mapping columns using SQLAlchemy's types to establish the connection between your Python code and the Snowflake database schema. For example, a user table might have columns for ID, name, and email. Here's a Python class defining this model. Notice the class inherits from base, which comes from declarative base. This is object relational mapping in action, connecting your Python classes to database tables. Snowflake offers specific types like varchar with large capacities for strings, ensuring efficient storage of your data. By defining models this way, you create a clear link between your Python code and the Snowflake database schema. SQLAlchemy allows you to perform create, read, update, and delete operations using intuitive ORM methods. These operations are managed within transactions for data consistency. To create new records, use session.add to stage the object and session.commit to save it to the database. For reading data, use session.query with filter conditions to retrieve records. This example fetches all users named Alice. To update records, modify the object's attributes directly and commit the session. To delete records, use session.delete followed by commit. This removes the object from the database. All these CRUD operations are managed within transactions to ensure data consistency and integrity. Consider an e-commerce platform where we have order and product models linked by a many-to-many relationship. This allows each order to contain multiple products, and each product can appear in multiple orders. Here's a sample table showing how the data might look. The orders table connects to products through a junction table for the many-to-many relationship. Using SQLAlchemy, we can query all orders that contain products in the electronics category with this ORM query. The join handles the many-to-many relationship automatically. Snowflake's query acceleration optimizes these complex joins, making ORM queries efficient even with large datasets. Best practices when using SQLAlchemy with Snowflake include several key considerations to ensure efficient, cost-effective, and performant database interactions. First, implement connection pooling to manage Snowflake's compute costs. Connection pooling reuses database connections instead of creating new ones for each query, reducing overhead and minimizing warehouse credit consumption. In SQLAlchemy, this is handled by the engine's pool configuration. Second, Snowflake's architecture relies on micropartitions and clustering keys for efficient data storage and retrieval. When designing schemas, incorporate clustering keys to group related data, improving query performance. SQLAlchemy doesn't automatically handle this, so plan your table structures accordingly. Third, understand Snowflake's columnar storage and micro-partitioning. This differs from traditional row-based databases, so optimize queries for analytics workloads. Monitor execution plans and leverage Snowflake's query acceleration features. Fourth, while SQLAlchemy simplifies many tasks through its ORM, be prepared to use raw SQL for advanced Snowflake-specific features like semi-structured data handling or complex analytical queries. This ensures optimal performance when the ORM abstraction isn't sufficient. Finally, regularly monitor query performance using Snowflake's query history and profiling tools. This helps identify bottlenecks and prevents unexpected warehouse credit overruns, ensuring cost-effective operations. The integration between SQLAlchemy and Snowflake is evolving rapidly. Expect deeper integration with SQLAlchemy 2.1's async features for real-time analytics. Snowflake may introduce native ORM support in Snowpark, reducing reliance on third-party dialects. This partnership will continue to simplify data workflows, promote data democratization, and drive innovation in cloud data management. Thanks for watching.